two back-to-back talks on quantum learning. Our first talk is on learning open quantum systems by Laurel Oos. Take it away.
Okay, thanks for the intro. So I'll be talking about this new work. This is joint work with Yuan Tang and John Wright, and it came out on Archive about a month ago. Okay, so first let's just consider some quantum system that doesn't interact at all with its surroundings. This is called a closed quantum system. And closed quantum systems evolve according to the Schrodinger equation, which takes this form for some Hamiltonian h. And when the Hamiltonian is time independent, then you can solve this differential equation, and it has the following solution. And so what this tells us is that if you start at some initial state rho at time 0, and you evolve under this time evolution operator, then that tells you what the state is at time t. Okay, but oftentimes in reality, then your system isn't totally isolated, and it actually interacts with some surrounding environment. This is called an open quantum system. And when the interaction between the system and the environment is like weak in a sense, or the environment is like forgetful or Markovian, then the dynamics are governed by Lindbladian. So that's what I'm saying is this L here. For now, we've seen a little bit of Lindbladians earlier in the week, but for now it just suffices to consider this as some superoperator that's a generalization of the Hamiltonian for open quantum systems. Okay, and if you solve this Lindblad master equation, then similarly to before, you can have some form for the dynamics under this Lindbladian. And the goal of this talk is to answer the question, can we learn an unknown Lindbladian from access to its dynamics? So if you can apply e to the LT for any time t, any initial state you want, then can you learn some full description of the Lindbladian L? And of course, we answer this in the affirmative. We give very efficient algorithms for doing this task for a wide class of Lindbladians. Okay, before I get into the results, let me motivate for you like why you might care about this problem. So one is that it's like a very natural generalization of Hamiltonian learning, which is like a very well-studied problem, especially for the past few years. But to give some more kind of applications, some of these also hold for Hamiltonian learning. One is learning effective Hamiltonians or Lindbladians. So a lot of big breakthroughs in physics kind of come from this idea of an effective Lindbladian, or effective Hamiltonian. And what happens here is that you observe some phenomenon in nature. And of course, the laws of physics will tell you everything you want to know. And this might be in the form of some like very complicated Hamiltonian that has like a lot of interaction terms and is just in general very hard to understand. And so it's often useful to then like throw out some of these interactions and just distill it into some simplified or effective Hamiltonian, which still captures the relevant physics. Okay, and most of the time this has been done by just on like pen and paper, doing a bunch of like physics approximations. But Hamiltonian or Lindbladian learning can be seen as like an algorithmic approach to this. And another application, perhaps more concrete, is for calibrating or benchmarking quantum computers. So our quantum devices have been seeing a lot of progress in their engineering lately. In order to continue to improve them, then we need to be able to fully characterize a device's behavior. And this was one of the original motivations of Hamiltonian learning, but one might argue that actually the Lindbladian is a more well-motivated or more realistic model for a quantum device, because your device will never be like fully isolated from its surroundings. Okay, and so Lindbladian learning might provide a more accurate characterization of your device and also help you to learn the Markovian noise. Okay, so I've just kind of told you like, oh, why you might care about the problem, but in the rest of the talk, I'll more precisely go over like the actual definition of the problem as well as our results, and then I'll talk about the algorithm and some of the proof ideas. Okay, so first for the problem definition. So I'm just going to write down this form of the Lindbladian. So the first term here, this is like the same as the Hamiltonian. Here I'm just decomposing the Hamiltonian and the Pauli basis. That's all that's happening here. And then in the second part, I'm also decomposing in the Pauli basis for like superoperators. And this anti-commutator part is just to ensure that you're trace preserving. Okay. And if this looks scary, like don't worry, the only thing we really care about are these like coefficients. And so the first part is sometimes called the coherent part. Sometimes I'll say this. And the second part is called the dissipative part. So the coherent part, again, just models the same thing as Hamiltonian evolution. And the dissipative part models the interaction between the system and the environment. Okay, and we consider a class of local Lindbladians. And here local means, so k local means that each of these terms only acts on at most k qubits. And we also consider degree d interactions, which means that each qubit is acted upon by at most d terms. Okay, so here's a picture. So consider these like 6 qubits in sort of a ring. Then the nearest neighbor interactions are satisfy these 2 constraints, because here each of the dots are the qubits, each of the lines are the interactions between any of these 2 qubits. And we can see that this is too local because each term is touching at most 2 qubits. And moreover, each qubit is touching at most 2 lines. Okay, and so the reason why we call it degree d is because it's really the degree of this like underlying interaction graph. Okay, and again, the goal here is given access to this dynamics, e to the LT, then can we learn each of these coefficients in the Pauli basis, these like alpha p and d p1, p2, to epsilon error. And there are 2 kind of variants of this problem. One is called parameter learning, and in this case, you know which alpha p and d p1, p2 are non-zero, and the only thing that you need to do is estimate them up to epsilon error. But there's also the harder problem of structure learning, and in this case, you don't know which alpha p and dp1, p2 are non-zero. And so not only do you have to estimate them to this epsilon error, but you also need to identify the large coefficients. And so in other words, you need to learn like the underlying interaction graph. So again, here's your picture of your 6 qubits. And a priori, because you don't know which interactions are actually in there, then you could, a priori, have like all of these 2 local terms. Okay, but you're promised beforehand that your unknown Lindbladian, the true Lindbladian, has bounded degree. So it could actually be that nearest neighbor graph that we saw before, or it could be this like next nearest neighbor graph. Okay, and a good structure learning algorithm should be able to distinguish between these 2 cases. And of course, you might think like, oh, okay, well, I can just estimate all of these like 2 local interactions, and that will perform structure learning. But the point is that the algorithms we develop in this work will be like much more efficient than just estimating like all possible k-local interactions. Okay, and remember that this is our goal, and there are several performance criteria that one might care about optimizing here. One is the total evolution time. So throughout our algorithm, then we'll apply e to the LT for like several different times. And so the sum of all of these times for which we apply it is the total evolution time. And comparing to like standard result or the state-of-the-art results in Hamiltonian learning, but replacing Heisenberg limit with standard quantum limit, then ideally you might want something, you might hope for something like d log n over epsilon squared. Okay, and note this is like really efficient because the scaling with system size is only logarithmic. So as you scale to like larger and larger systems, the efficiency is like very weakly dependent on n. And another thing you might care about is the time resolution. So this is the minimum time for which you apply e to the LT. And this actually you might want to be large. And this is because experimentalists tell me that it's kind of hard to turn on the dynamics and then like immediately turn it off. Okay, so to make it easier for them, you want this to be quite big.
Excuse me.
Mm-hmm. Yeah.
What is D?
Oh yeah, d is still the degree. So each qubit only acts on at most d terms, or is acted upon by most d terms. Yeah, and again, kind of turning to the Hamiltonian learning literature, you might hope for something that's like 1 over d. And you should kind of think of d as like a constant for us. So this is like actually a very large time resolution. So it's like a constant. Okay, and the third metric that you might care about is the classical post-processing time. This is kind of self-explanatory. And of course, you would hope that this is polynomial in all of the relevant parameters. And I'd also like to note that some works consider a different setting called the sparse setting, in which instead of any locality constraints, then you only have some like upper bound on the number of terms in your Lindbladian. So this is like arguably more general because you don't have any locality assumptions, but they pay for this by having a total evolution time that scales polynomially in the system size instead of only logarithmic. So this sparse setting is like somewhat incomparable to ours. Okay, and there's been a lot of work in the past on Lindbladian learning. I'm just going to mention a few of the representative works. And their results fall into two main categories. So one is that they do structure learning, but for very restricted settings. So in particular, this like Stilich-Franca et al. Paper, they do structure learning of Lindbladians, but only when the dissipative part acts on single qubits. Okay, so it's like quite restrictive. And the second case is where they do parameter learning, but the complexities are like very suboptimal. So they're like very far away from this d log n over epsilon squared that I said that you should kind of hope for. Okay, and so no one has managed to do structure learning even with good complexities. And meanwhile, for our work, we achieved the stronger task, the harder task of structure learning from access to the dynamics with a total time evolution that scales like d cubed log n over epsilon squared, and this time resolution, which is like 1 over d. And again, you should be thinking of d as kind of like a constant, so the time resolution is big, and our total time evolution is like log n over epsilon squared. Okay. And I should also note our results are actually a lot more general than this. So I'm only stating the result for like bounded degree, like strictly local Lindbladians. But it actually also works for Lindbladians with long range interactions. And so I won't talk about those results in detail, but you can check out the paper for it. And also we get some interesting results in Hamiltonian learning. So for the past few years or so, there's been this problem of structure learning Hamiltonians from access to Gibbs states that's been kind of floating around, and no one had made any progress on it. And it's arguably one of the biggest open questions in Hamiltonian learning. And here we make the first progress on this problem, where we get structure learning of Hamiltonians from high temperature Gibbs states. So here, instead of access to the dynamics, you're given access to a more like static property of your Hamiltonian, which is the Gibbs state, copies of the Gibbs state. And as long as the inverse temperature is like smaller than some threshold, then we can perform structure learning with this like optimal complexity. Okay. And yeah, so this is like the first efficient algorithm that is able to do this structure learning task. Okay, and another thing I'd like to emphasize is that the quantum part of our algorithm really only requires like very simple experiments. And so in particular, all it requires is like preparing some random Pauli eigenstate, so that's like what these blank blocks are, evolving under your unknown Lindbladian, and then measuring in some random Pauli eigenbasis. Okay, so it's like very simple, just a prepare, evolve, and measure sort of circuit, no adaptive queries, no quantum control. Okay, and there's also been like a lot of excitement about Lindbladian learning. Many of you may have noticed that there was a lot of concurrent works around the same time that our paper was released. So I'd like to take the time to kind of say what the differences are. So first, there were these two works by Romanov et al. And also by Sinha, and they consider this like sparse setting, which remember I said before is like a bit incomparable because while they don't have any locality constraints, they pay for this by like a much larger total evolution time. Okay, so this is kind of incomparable to our work. And then there were these other works by Arad et al. And Mobus et al., which do structure learning for local Lindbladians with around the same complexities as us, except note that their dependence on the parameters is much worse. So they get this d to the 2k factor in their total time evolution. Whereas remember, ours was just a d cubed, which is like fully polynomial. Okay, and they also lose some log factors. And I also have this like star around the structure learning because the Arad et al. Paper, they do structure learning in the sense that I've kind of presented here. But the Mobus et al. Paper has kind of a different type of structure learning result. where their complexity depends on like the gap between large coefficients and small ones. So it's kind of a bit different than ours. Okay, and also the Arad et al. Paper only works for this like strictly local setting. But the Mobus et al. Paper actually does work for long-range Lindbladians, but only in the easier task of parameter learning. Okay, and meanwhile we get structure learning. And to be completely transparent, those two papers have beat us in the classical post-processing. So they have polynomial classical post-processing. We only have quasi-polynomial, but we know how to fix this, and you should stay tuned for our V2. Okay, so just to sum up that comparison, so we see that in the total evolution time, they have this like d to the 2k, both of them, whereas we have the fully polynomial d cubed. Everyone kind of gets the same time resolution. And for structure learning, we all get structure learning minus this like caveat on the Mobus et al. Result. For long-range Lindbladians, we're the only ones that get structure learning. And for the post-processing, we are losing a bit in this quasi-polynomial. But like I said, you shouldn't worry too much about this. We know how to fix it. Okay.
Laura, quick question.
Yeah.
Are there algorithms similar to yours, or are they totally different?
There are like some aspects are like similar. Some are not. So they use like polynomial. So yeah, they use like polynomial interpolation, both of them. I think that this is like the main difference. It still ends up getting the same time resolution, but I don't think any of them use our like I'll show later our algorithm, and we use like some convex optimization techniques, and I don't think any of them are using that. Yeah. Any other questions before I move on? Yeah.
So the Hamiltonian result, learning result that you had mentioned from high temperature gives states, intuitively why it's easier to have high temperature give states as opposed to low temperature? I thought that the former would be closer to like what's next.
Oh, I would have thought low temperature is like a lot harder because it's like closer to ground state. But I guess the reason like why our algorithm is basically the same for high temperature Gibbs states is because like real-time evolution and high temperature Gibbs states are like kind of analogous because the cluster expansion still converges for high temperature Gibbs states. Yeah. Yeah.
In the work that also dealt with this easier parameter learning task, do you know if they can achieve like some kind of improvement in the total time evolution, or?
No, I think our complexities are pretty much the same, but we just get structure learning. Yeah, I think generally you should kind of expect that the total time evolution for structure learning should be the same as parameter learning, but it's just like a lot harder to get. Yeah?
Do any of your parameters depend on locality?
Yeah, so we have like some constants that depend on the locality. We didn't try to optimize the dependence on k at all. You should really think of k as a constant. But either way, even if k is a constant for these things, then it's like, yeah, it's like some parameter to a constant, so it's worse. Yeah, okay. So now I'll talk about the algorithm. So at a high level, this is kind of what happens. So first, we perform like several of these experiments that I mentioned before about like preparing some random Pauli eigenstate, evolving under Lindbladian, and then measuring in some random Pauli eigenstate. And so we repeat this a few times to collect enough data, and then we throw this into some like classical post-processing to get out some description of the Lindbladian. Okay, and let me unbox like a little bit about what this classical post-processing is doing. So first, it'll take the data from these experiments and kind of post-process them into being some expectation values that we actually care about. Okay, and then what you'll do is you'll like guess what you think the Lindbladian parameters are, and then compare against the expectation values from the estimates and kind of update your beliefs based on this comparison. Okay, that's like the overall sketch you should have in mind. And let me formalize this. So For the rest of the talk, I'm just going to consider fully dissipative Lindbladians, so I don't have like that first coherent term that was like the Hamiltonian part. Our work does work for if you include a coherent part, but it's just easier for the sake of presentation to just consider the fully dissipative Lindbladian. Okay, and I'm just going to consider some vector of expectation values, which depend on like the parameters of the Lindbladian here at D. I'm not going to tell you what these expectation values are yet. I'll tell you them in like a few slides, but for now it's not really important. Okay, and the point is that you can compute these expectation values for an unknown Lindbladian, the true one, corresponding to those parameters D. And you do this by those experiments that I mentioned about like prepare, evolve, measure. And you can also compute these same expectation values, but for your guessed parameters. So these I'm calling X. And you can do this classically, okay? Maybe just by like simulating the Lindbladian evolution classically. I'm not talking about time complexity here, but just like information theoretically, you could compute these. Okay, and the point is that you want to find some parameters X such that the expectation values for those for that Lindbladian L sub X matches the expectation values from the true unknown Lindbladian. Okay, and that's how we tell like if our answer is correct. In other words, we want to find the zeros of this function, this like f function, where the reason for this like 1 over t factor will become clear later. Okay, so this is like the overall goal. And in convex optimization, there's this like somewhat well-known method to try to find zeros of a function. So let me tell you a bit about that. This is called like Richardson iterations. So just consider some like scalar function. So our f on the previous slide was vector valued, so it comes with like its own complications, but let's just consider some scalar function for now. The way that Richardson iterations work then is you initialize at some point, which I'll call like x0. And then what you do is you update your estimates by just subtracting off like how wrong you were. So remember f is like the difference of two things. So yeah, you're subtracting off like how far you were, multiplied by some step size eta, where this choice of step size is like pretty important. So let's do an example for a linear function where f of x is just equal to like ax minus b. Say you know the slope, then taking the step size to just be like 1 over a converges immediately. The reason why is like pretty obvious. So this is like the definition of the Richardson iteration, taking the step size, plugging in what f of x is as just ax minus b, you get this. And the 1 over a and the a cancel, and so the x, the first two terms cancel, and you're just left with a b over a. Okay, which is obviously the zero of this linear function. Okay, so in other words, for a linear function, taking this step size, you just converge immediately in one step. So if you start off at 0, using the step size, you just immediately get to the 0. Okay, what about for more complicated functions? For a smooth function, f, we can just use tangent lines to do the same thing. So again, here's a picture of like a square root function. We start off at this initial point and consider the tangent to the curve at this point. Then what we can do is we can run the Richardson iteration for this line, which gets us exactly to the 0 of the line. And then we drop this down to the curve and use that as the new iteration along the curve. Okay, and we can repeat this using the tangent line at this new point, dropping that 0 down to the curve, and so on. Okay, and you can see we're getting closer and closer to the 0 of the function. Okay, so this should work. And the point is that our algorithm is like inspired by this sort of Richardson iteration. Okay.
How is it different than Newton?
Yeah, I guess it's Newton.
Yeah, it's kind of, it is different because in Newton's iteration, then you usually have a Jacobian term, inverse Jacobian term. Meanwhile, this is just a first order method. So it's like much simpler. I guess Newton's also has like quadratic convergence, so it's like much faster convergence. So you'd expect to get to within epsilon with like log 1 over epsilon iterations. Meanwhile, Richardson is just a first order method, and it only has linear convergence. So you get within epsilon distance of your solution with log 1 over epsilon iterations.
So does Newton not work for some reason in your setting?
Newton, I think for learning Lindbladians, I think it's not clear that Newton works. Like, I think it's feasible that it does. I guess this is a good point that this previous work by Ha, Kathari, and Tang on like learning Hamiltonians from high temperature Gibbs states and from real-time evolution, they actually use Newton-Raphson to solve their thing for Hamiltonian learning. But yeah, I think it's not clear analyzing the Jacobian if that works as nicely in the Lindbladian case. And another point is that HKT only works for parameter learning. And so it's non-trivial to extend this to structure learning. And we found that like Richardson kind of works a lot nicer for this. Yeah.
Sorry, do you first show that script F is like strictly concav?
Yeah. Essentially we need, essentially our proof shows that like F is strongly convex. I should also note in HKT, while they actually do use Newton-Raphson, their complexity actually doesn't use this quadratic convergence property at all. Like they actually just show that it converges in a log 1 over epsilon number of iterations. So it's kind of like they're not really using like the key point of why you should use Newton-Raphson. Like I believe they should be using Richardson, really. Okay. So remember that our function takes this form. Okay, so it's like a difference of two expectation values. And the point is that if you can show that f is approximated by some linear function, so here remember that this is like a vector valued function, so our slope here is like actually a matrix, capital A. If you can show this, then kind of by the intuition I gave on the previous slides, then A inverse is somehow like the right step size to choose. Okay, so I'm being like a little bit hand-wavy about this because again, we're dealing with a vector valued function. It's not really clear that like this like 1 over little a that I had before actually works for A inverse, but you'll have to trust me on this. And I would also like to note that the sense of approximation we have here is like a lot stronger than I had in the previous slide. So in the previous slide, we were kind of finding these like tangent lines at each point, and the slope of those tangent lines was different at each of those points. But here I'm actually saying that regardless of the input, x, then you can still approximate this by like a linear function with the same matrix A. Okay, so A doesn't depend on what point you're at. Okay, so this is like a much stronger sense of approximation. And then our algorithm is effectively, okay, we initialize at 0, and then you just update your beliefs based on this like sort of Richardson iteration. Okay, so instead of the step size being like the 1 over little a, I have A inverse. Okay, and I'm kind of hiding something, so the algorithm is actually like a little bit more complicated than this, but for the sake of this talk, then yeah, it suffices to consider this, and you can ask me about it afterwards or read the paper if you want to see the real algorithm. Yeah?
You were saying earlier, you were talking about a scalar function, now this function outputs vector. Like,
Yeah.
Why don't you take like the difference of the two vectors, like its norm or something like that? Like, then you could get a scalar.
I think it's not clear to me that that would be enough. Yeah, because like I think you really do want the parameter values to match for like all of these different expectations, I think. Yeah. Yeah, I'm not totally sure, but I think that, yeah, I'm not totally sure. Okay. Okay, so now let me actually tell you like what those expectation values were. I've kind of just been referring to them as like some vector E, but I haven't really told you. So consider these expectation values, just like trace P e to the LT of Q. So these are just like entries of your Pauli transfer matrix. And for P and Q local, then you can estimate these via random Pauli measurements. Again, the same picture of prepare some random Pauli eigenstate, evolve under Lindbladian, and then measure. And it's really crucial here that like P and Q are local in order for this to work efficiently, to be able to estimate like many of these expectation values in parallel. And the reason is because if you're preparing some like random Pauli eigenstate, this will actually be an eigenstate of like P or Q with like very low probability unless P and Q are local. So this is like the same reason that classical shadows with random Pauli measurements only works for predicting local observables. So this is kind of like a quantum process version of that. Okay, but these aren't actually the expectation values we consider. We consider expectation values of this form. So it's like a little bit different. The main difference, I guess, is that we're taking the Pauli at random from this set that I'll tell you about later. And so the like input to the Lindbladian is this random Pauli, and also the like output also depends on this R. Okay, and the set S is just like the joint support of P1 and P2. Okay, and we want to compute these expectation values for all P1 and P2 with this joint support of size less than K. Okay, so because P1 and P2 are local here, then the same argument that I gave on the previous slide about like random Pauli measurements allowing you to estimate these efficiently works for these expectation values as well. Okay, so we can estimate all of these for all of these like K local P1 and P2, and we can shove them all together into some vector, and that's what I've been calling this like vector E this entire time. And the key thing that we need to prove is that you can approximate these expectation values by d times, or sorry, the time t times a times d, where d is like the vector of dissipative coefficients, and a is this matrix that I still haven't really told you what it is. Yeah, so this is what we want to show. And this implies that what we needed from before, that f is like approximated by some linear function, just because remember that f is just like the difference of these expectation values, and so you can plug in the lemma for each e of x and e of d to get this. Okay, and this is also why we need the 1 over t factor, just to cancel out this t here. Okay, so now like the rest of the talk will just be talking about how you prove this lemma, roughly. Oh, I guess were there any questions about this? Oh, yeah.
Why does it suffice for our Lindbladian to match these expectation values?
Yeah, I guess this is like, I guess in Hamiltonian learning, there's kind of this thing about like sufficient statistics that like matching, if you can match the Hamiltonian at all of these, on all of these expectation values, then this is like enough. I'm kind of, yeah, relying on that sort of statement for Lindbladians here. This was this paper by like Anurag, Arun Shalam, and others. Okay. Yeah, I guess we don't use that like black box, but we kind of show something similar that like this is enough for Lindbladians, morally similar. Okay, so let me talk about how we might prove this lemma. So what it really relies on is some like series expansion. So consider your time evolution superoperator, this e to the LT. You can just Taylor expand and write this as like identity plus some linear term plus some higher order terms. But the point is that for very small times, then the linear approximation is actually good enough, right? Because then this t squared, these t squared in higher terms, just become like too small to matter. Note, however, that our algorithm worked for like these larger times, like our time resolution was 1 over d, and so we don't actually use this like small time approximation. But yeah, for the sake of this talk, then this will suffice. We have to use like a more complicated sort of argument and series expansion for the long time case. Okay. So remember that our expectation values are of this form. Then using the linear approximation, then we can just write it as this. So here, this is the term coming from identity. This is the term coming from the linear term. And notice that the first term actually just goes to 0. And why is that? It's because R here, remember, it has the same, is also supported on the support of P1. And so if you try to commute R past P1, then it'll pick up like a -1 with probability 1/2 and a +1 with probability 1/2, because it's a random Pauli. And so in expectation, this goes to 0. Okay, so we're just left with the linear term. Okay, so we can just consider these expectation values for now. And the lemma then reduces to showing that those expectation values, where you just take the linear term, give you out some like t times a times d. Again, for this like mysterious matrix A that I'm about to tell you about. Okay, so the point is that you can always write the Lindbladian in this form.
Excuse me, is it true that a T is forgotten in the first slide?
Oh, yes, there should be a t here. Yeah, good catch. Okay, so we can always write the Lindbladian in this form. So here I'm just decomposing your like superoperator in the Pauli basis for superoperators. It's just easier to write it like this. And I'm going to define some like, suggestively define some basis functions. So these like chi, q1, q2 of R. And these are like orthonormal basis functions. And so you can really think of writing it like this as like d, q1, q2 are like the Fourier coefficients of your Lindbladian. Okay, and I'm actually going to consider the diagonal form just to make it a bit easier. So by diagonal, I mean that q1 is always equal to q2. So we just have qrq. Okay. Then when we look at these expectation values from up here, just plugging in the form of the Lindbladian, pulling out the sum, then we get this. Okay, and because I told you that these basis functions are orthonormal, then that's great, because it'll just pick out like a delta function when p is equal to q. So we get dpp. So it picks out just like one distributive coefficient, and you're like, okay, this is great, because the A matrix now is just identity, and it's like easy to analyze, it's like well-conditioned, all of that stuff. Except that's not actually what happened. Note here that the expectation here is only over R in some support. So if R was like a global Pauli, global random Pauli, then what I just told you would be true. But because we have to restrict R to be local in order to make our measurements like easily parallelizable, then this is not true. So the basis functions are actually not orthonormal when you only look at this like restricted expectation value. And let me tell you why that's not true. So this is like the equation from the last slide. The point is that local R actually can't tell the difference between some p's and q's. So if p is just x on this like third qubit, and q is like the same thing except y, it has like an additional Pauli y on the fourth qubit, then R, because R is only supported on the support of p, it's only looking at this third qubit. And so it kind of can't tell what's going on, that there's like an extra y here by accident. More precisely, QRQ is equal to PRP, right? Because again, R is only supported on the third qubit, and so you can commute the y from Q past R, and so they cancel. Okay, and remember that like QRQ is just the definition of this chi QQ of R. So again, these are not orthonormal or orthogonal. Okay, and the point is that we just pick up extra like DQQ terms whenever Q contains P. So by contains here, I mean that Q has like a larger support than P, but agrees with P on its support. Okay, and in general, I think I'm also missing a T here. In general, then we show the following, that so far I've just been working the diagonal case, but in the non-diagonal case, then this is what happens. So you pick up this like extra sum of D, Q1, Q2 terms, where by like this symbol, I just mean that Q1 and Q2 agree with P1 and P2 on their support, and agree with each other outside of the support. And the reason why they have to agree with each other outside of the support is so that this like commuting past R and then canceling happens. Okay. And this transformation on what D is exactly the matrix A. So that I can finally tell you what A was this entire time. It's just that A acting on D gives you this sum. Okay, any questions about that? Okay. And here, I guess I'd like to highlight that it would have actually been really nice if this actually happened. And I feel like all of the challenges of Lindbladian learning really come from the fact that this A matrix is not identity. And yeah, you can ask me more about why that is later. But the other reason also why we can get Hamiltonian learning results really easily is because in the Hamiltonian case, even when you take these expectation values to just be local, then you still get that A is the identity matrix. Okay, so this is like why Hamiltonian learning is like kind of easier than Lindbladian learning. And it just makes the algorithm like a lot easier to analyze. And so we kind of get this like learning from high temperature Gibbs states result for free, essentially. Okay. So yeah, I'll just sum up then. So overall, we proved some very general guarantees for learning Lindbladians from access to the dynamics. And these are applicable to like long-range Lindbladians and also this like strictly local case. So in particular, it applies to like the quasi-local Lindbladians that people care about for Gibbs state preparation. And as a special case, we also get like the first efficient algorithm for structure learning Hamiltonians from high-temperature Gibbs states. Okay, and there are some open questions. So one is like, is there a fundamental difference between the complexities of Lindbladian and Hamiltonian learning? I guess notably, like our algorithm has this like d cubed dependence on the degree, whereas I was mentioning that like in Hamiltonian learning, you just get a d. I think we think that d cubed can be improved to d squared, but it's not clear if you can do any better than that.
Where does the d cube come from?
It's like a bit hard to say. I guess yeah, I think it like gets a bit technical. It's essentially in this like approximation argument of like when can you approximate f by like its linear term. Yeah. Yeah, I guess like that approximation only holds for like a certain time resolution, and then that time resolution comes into our total evolution time as like a d cubed. Or actually, it should come in as like a d squared, and the extra d is coming from kind of converting norms at some point in our error analysis. Okay, and another open question is, can one design algorithms for efficiently structure learning Hamiltonians from access to the Gibbs state at any temperature? So here we only got it for the high temperature regime, but the low temperature regime is like totally open because as I mentioned before, cluster expansion techniques only really apply in this high temperature regime. And even like the task of parameter learning Hamiltonians from Gibbs states at low temperatures was like really hard. Like it was this really long, it was like this long plenary at QIP a few years ago. So the structure learning thing should be even harder. Okay, yeah, and that's all. Yeah.
Can you go back a couple of slides?
Yeah.
I think I'm missing something here, but over here you said that in the Hamiltonian learning setting, A turns out to be the identity.
Yeah.
I guess I'm still a bit confused. Don't you still have this like locality issue with your polys where you might pick up some terms on the places where their supports agree on like this Q1, Q2?
You actually don't run into this issue. So I guess the expectations, I guess one way to see this is that in Hamiltonian learning, there's like a particular choice of like input Pauli and like output that you measure, like these P and Q that I had before, such that you can isolate a single Hamiltonian coefficient alone. And the way you choose these Paulis is like, you choose one of them to be just like, okay, some Pauli that doesn't commute with the term that you're trying to estimate. And then the other one is like that Pauli times the term. And so this will just, isolate directly one coefficient. And so you don't even need the randomness to like do this sort of thing.
Maybe another way to see it in this case is like the Hamiltonian terms are like the ones where maybe P1 is non-identity, but P2 is identity. And then the Q's that you're going to confuse it with are ones that are the same on the support of P, but then have extra things outside the support of P that agree with each other. And once you have two things outside the support that agree with each other, it's no longer a Hamiltonian term, it's a Lagrangian term.
I guess you had your hand up first.
Yeah, so I wanted to ask how strongly this like linear approximation has to hold because, like you said, Richardson integration for linear functions like one shot. So why, if it's strong, then why am I not just forming, I don't know, A inverse D or something?
Yeah, so I guess, I think it's because of the approximation. Because while I've just been writing this like approximation symbol, the error actually depends on like how far your estimate is from the true parameters. So you can kind of bound like the error of like how far f is away from that linear term by like something in terms of the distance between x and d. Okay, and so that's why you kind of have to like refine your estimates so that you get like closer and closer. So it's not just like a you can bound this approximation error by some constant.
But somehow this looser approximation is sufficient to choose the step size as A inverse.
Yeah. We essentially have to like analyze the norm of A and make sure it's like well conditioned. In order to make this work. Yeah, I'm kind of brushing a lot under the rug. Yeah.
Can you show this slide, structure learning?
Yeah. It's gonna be far back. There's like 120 slides. So, okay, getting close? Okay, yeah.
A little bit.
Okay. Here?
Here.
Okay.
Okay. Thank you.
Okay. Nice. Andrew?
So where does the quasi-polynomial classical post-processing time?
Yeah.
Sorry.
No, I think this is closer. Okay, so it comes from this that I threw under the rug as well. So I said that like, you can estimate expectation values. You can just estimate these expectation values classically. And I was like, okay, just ignore the runtime and just say like, you can do this by simulating the Lagrangian. That's where the quasi-polynomial runtime comes in. Essentially, the way that we do this is you only need to estimate these. You don't need to compute them exactly. And so you can do like a cluster expansion, like some series expansion of like e to the LT. And then you can truncate it at a high enough degree and compute each of the terms in this series expansion. And each of, I think like, computing each of these terms is like quasi-polynomial for us. But yeah, again, don't worry. It'll be fine. Yeah.
Thanks for the talk. Really nice. I'm curious if you could say more about the second open question. Is there hardness results for it? Is it do these results here require like correlation decay, these types of properties that you get at high temperature?
I guess like I said, then the reason why it only works at high temperature is because the cluster expansion only works at high temperature. So like our techniques kind of just die in the low temperature regime. So I don't think there would be hardness results because you can do parameter learning in the low temperature regime. And I would kind of expect, because you can do parameter learning quite efficiently, that like there must be some way to do structure learning. Like I don't know of any examples in the literature where like you can do parameter learning, but you somehow can't do structure learning. I would find that like kind of surprising. Yeah. One thing I should also mention actually is that like this quasi-polynomial runtime thing, this is only for the Lagrangian learning from dynamics part. In the high temperature Gibbs state case, our runtime is polynomial already. Yeah. Yi?
I want to better understand the quantum part of the algorithm. Is it just take random Paulis conjugated by hand by
So it is just like prepare some random polyeigen evolve under Lindbladian, and then measure in a random polyeigen basis. Those are all like the quantum experiments we need to do to estimate these expectations. We like post-process them in a way such that it like ends up in that form that I had somewhere. This one, yeah. Yeah, so it's like only classical post-processing that gets us to like these expectation values, but like the quantum part is just the prepare, evolve, measure. Yeah.
In your comparison, it seemed like it wasn't possible, or it seemed like most of the work that we have for minimum evolution time is like 1/d.
Yeah.
So if I'm allowed, let's say I'm fine with poly post-processing and whatever else, if I just go to enough terms, can I get this better, or?
No, I think the issue is that the cluster expansion just like does not converge for times larger than like 1 over like k times d or something. Yeah, I think like maybe, I guess like in Alexander's talk yesterday, yeah, he mentioned this like Barbanach interpolation thing, which is basically like an analytic continuation of the cluster expansion for like larger times. I think you have to be careful about like where the zeros are for that to work. But this would still also only get you maybe up to like any constant time, because when you do this Barbanach interpolation thing, then the truncation degree blows up exponentially in the time. So you couldn't do this for like larger than constant times. I will say, I think there's like some works in Hamiltonian learning that try to do larger time resolutions, like this one by like Constantine and Robert and I think someone else. Yeah, but I don't know that paper in depth. But I think they try to get Hamiltonian learning from like maybe like polynomially long time resolutions. Yeah.
So just to make sure, so this algorithm is very non-adaptive in the sense that the time I evolve each time is like I just pick a parameter before and I just do like many runs or something.
Yeah.
Okay.
Yeah, and there's like no interleaved control, like interleaved quantum control, which you might expect from Hamiltonian learning. But I guess the reason is because in Hamiltonian learning, you want to get like Heisenberg scaling, like the 1 over epsilon. And so you kind of need this like quantum control to do that. But because Lindbladians are like quantum channels, you only, they're like lower bounds, so you can only get like 1 over epsilon squared. And so for this, we don't need any control. Yeah.
So maybe this question was already asked. It's about your second open question.
Yeah.
If you have this technique for learning Lindbladian, why you cannot use the same for learning Hamiltonian?
Yeah, so I guess we do use it for learning Hamiltonians from high temperature Gibbs states. Yeah, so this was like the second result that I mentioned, but the issue is that our techniques heavily rely on this like series expansion, which only works at high temperatures.
All right, if there are no further questions, let's thanks for the speaker.
Can I ask the same question here?
Oh yeah, no problem.
So